In this lesson we'll learn our first derivative formula, and here it is highlighted, and it tells us that the derivative of x to the power of n is n times x to the power of n minus 1, where n is a positive integer. Now, in order to be able to use this formula, we're first going to have to prove it. And after we prove it, we'll see some examples of its use. Before proving the formula, we're going to introduce another formula that not all of us may know. And that is that a to the power of n minus b to the power of n is equal to a minus b times a to the power of n minus 1 plus a to the power of n minus 2b plus a to the power of n minus 3b squared. I think you can see where this is going, right? Plus, at the end, we will have b to the power of n minus 1. Now, this formula is very easy to prove because we just expand the brackets. If we expand the brackets, we start by multiplying a with all the terms in the second bracket. We get a to the power of n plus a to the power of n minus 2 times a to the power of 1, which is a to the power of n minus 1 b, plus a to the power of n minus 2 b squared, plus the last product we have is a times b to the power of n minus 1. Now, we multiply all the terms in the second bracket with b, so that we get minus a to the power of n minus 1b minus a to the power of n minus 2b squared minus all the way to the end, and at the end we have b to the power of n. As we can see, we have many like terms. A to the power of n minus 1b minus a to the power of n minus 1b will be 0. A to the power of n minus 2b squared minus a to the power of n minus 2b squared will be 0, and so on. So we can eliminate all our terms apart from a to the power of n minus b to the power of n. This is the formula that we'll be using. Also, what we need to use in order to prove the derivative formula is the definition of the derivative. F dashed x0 is equal to the limit when x tends to x0 of f of x minus f of x0 over x minus x0. Our function in this case is f of x, which is equal to x to the power of n. So then, going back to our expression here, to the limit, we will have limit when x tends to x0 of f of x, which will be x to the power of n, minus f of x0, which will be x0 to the power of n, over x minus x0. And here's where our formula comes into play. So this is then equal to limit when x tends to x0 of x to the power of n minus x0 to the power of n will be equal, according to the formula, to x minus x0 times x to the power of n minus 1 plus x to the power of n minus 2 x0 plus x to the power of n minus 3 x0 squared. We need a longer fraction, plus, okay, all the way to the end, where we will have x0 to the power of n minus 1. This is over x minus x0, and what we can see here is an opportunity. We simplify x minus x0, thus eliminating the fraction. We have then is equal to limit when x tends to x0 of this sum, which is x to the power of n minus 1 plus x to the power of n minus 2 x0 plus x to the power of n minus 3 x0 squared plus, and right at the end we have x0 to the power of n minus 1. Now we will apply the limit, but we need some more space so we can eliminate the first formula. So when applying the limit, x tends to x0, so then we will get is equal to x to the power of n minus 1 plus x to the power of n minus 2 x0. X will be x0, so x0 to the power of n minus 2 times x0 will be x0 to the power of n minus 1. X to the power of n minus 3 when x tends to x0 will be x0 to the power of n minus 3. x0 to the power of n minus 3 times x0 squared will be again x0 to the power of n minus 1. Plus all the terms, they become x0 to the power of n minus 1. How many terms do we have? Well, we started from this first term where we had no x0, so we could have said that x0 was to the power of 0, and we ended up at x0 to the power of n minus 1. So from 0 to n minus 1, we have n terms. So we have n times these terms, which is equal to n times x0 to the power of n minus 1. What does this mean? It means that our derivative f dash of x0 was n times x0 to the power of n minus 1, where x0 can be any real number. So then we can safely say that f dash of x will be n times x to the power of n minus 1, and that is our formula. Now this was the proof. Where can we use this when differentiating? The truth is, we will use this formula a lot. Let's have an example here. F of x can be x to the power of 6. We no longer need to apply the definition of the derivative. If we want f dash of x, we will just use the formula. Our n here is 6, so it will be 6 times x to the power of 6 minus 1. In other words, 6x to the power of 5. This applies to any power of x. In fact, it's been proven, but that's a very difficult proof to provide, so we will just state the fact. It also works if instead of n, which is a positive integer, we have n, which is a real number. Even in the case of irrational numbers, the formula stands. So we could also use this for functions like f of x is equal to the square root of x, because the square root of x is actually x to the power of 1 over 2. So when we want to get the derivative, we'll use the same formula. 1 over 2x to the power of 1 over 2 minus 1. We applied the same formula, which is 1 over 2 x to the power of minus 1 over 2, which is 1 over 2, and x to the power of 1 over 2. We can take this aside and work with it. X to the power of minus 1 over 2 will be 1 over x to the power of 1 over 2, and we go back to what x to the power of 1 over 2 means. It's 1 over the square root of x. So then, going back to our exercise, the derivative is actually equal to 1 over 2 times the square root of x. This formula makes it very, very easy for us to find derivatives, and during the course of this mathematical analysis, as it's called, we will find many more fascinating such formulas. All the best!